Dear students, let's discuss some more examples of groups. These examples will include permutation groups as well. Recall that last time we discussed dihedral group of a square. Dihedral group of a square which had 4 rotations each rotation being through 90-degree angle. So 4 rotations and 4 reflections. So we obtained the dihedral group of square. We denoted it by D4 and we noted that number of elements in D4 is equal to 8. That is 4 rotations and 4 reflections. 8 is equal to 2 multiplied by 4. And next we discussed dihedral group of a regular pentagon. Dihedral group of a regular pentagon. And recall that in this case we had 5 rotations and 5 reflections. We obtained dihedral group of a regular pentagon and we denoted it by D5 and noted that the number of elements in D5 or order of this group is equal to 10. That is 5 rotations, 5 reflections. This is equal to 2 multiplied by 5. Let's note one thing from our previous session, that when we considered rotations for rotations of square, we divided 360 degree by 4 and we took rotation through 90 degree. Then again our first rotation was through 0 degree, that is the square as it is. Then we rotated it through 90 degree, then again through 90 degree, then again through 90 degree. So for rotation of a square we divided 360 degree by 4 and our angle of rotation was 90 degree. Also our reflections were through diagonals and lines joining midpoints of opposite sides We can just see it like this. This is about reflections. So our reflections were through diagonals. So these are 2 diagonals we took reflection through, and then through lines joining midpoints of opposite sides. So lines joining midpoints of opposite sides. So diagonals and lines joining midpoints of opposite sides. So these were the lines we took reflections. And let's recall about regular pentagon for rotations of regular pentagon. We divided 360 by 5 and we obtained 72 So this is the angle we rotated the pentagon again and again, few times in fact. And the reflections were through in this case reflections were through the lines joining each vertex to the midpoint of opposite side. So and reflections were through lines joining vertices with midpoints of opposite sides. Let me draw the diagram. Um, let's see, this is the pentagon. May not be very good diagram, but just to understand. So what we will do is that we will take one particular vertex. Suppose we take this vertex and this is the opposite side. We take midpoint of this opposite side and join this vertex with this midpoint, and we took reflections about this line. Next, suppose we take this vertex, then this is the opposite side of this vertex. We take midpoint of this opposite side and join this vertex with midpoint of opposite side. Similarly, we will join this with midpoint of opposite side. So this is the line we took reflections about, and next we can join this vertex with the midpoint of opposite side, and similarly we can join this one with midpoint of opposite side. So these were the lines we considered reflections about. So we can write these rules in general form as well, but before we must understand that in case of a regular polygon for which number of sides is even, we take reflections through the diagonals and lines joining midpoints of opposite sides. And for a regular polygon for which number of sides are odd, we take reflection through lines joining vertices with midpoints of opposite sides. So let's have a note about this thing. So for dihedral group of a regular polygon, for Dihedral Group of a regular polygon having n equal sides, in fact, sides of equal length, equal sides. We must note that n is greater than or equal to 3. We can have an equilateral triangle, then a square, then a regular pentagon, regular hexagon, and so on. So for dihedral group of a regular polygon having n equal sides, where n is equal to 3, if n is even, then the reflections are taken through diagonals, and lines joining midpoints of opposite sides. Joining midpoints of opposite sides. There will be n reflections. n upon 2 plus n upon 2. Because there will be n upon 2 diagonals and n upon 2 lines joining the midpoints of opposite sides. So there will be n reflections. Let me write it in bracket, and n rotations where angle is given by 360 degree divided by n. So this will be for even and odd both cases. And secondly, if n is odd, then the reflections are taken through the lines joining vertices with midpoints of opposite sides. Joining vertices with midpoints of opposite sides. And there will be n reflections, because there are n vertices, so you will obtain n lines joining vertices with midpoints of opposite sides. So there will be n reflections. And as above, n rotations, where angle being 360 divided by n. So again, there will be n reflections and n rotations, n reflections and n rotation in both cases. But in case the number of sides is even, this is the way we get reflections, and if the number of sides is odd, then this is the way we get lines of reflections. So finally we note that let dn be the dihedral group of regular polygon of n sides or regular n-gon. Sometimes we write it in this way as well. So let Dn be the dihedral group of regular n-gon, then order of Dn, number of elements in Dn is equal to n rotations plus n reflections, and this is equal to 2 times n. So this becomes formula for order of dihedral group. So this was about dihedral groups, or in fact this was revision as we had done in our previous session. So I am not defined the group so far. In fact, I am depending upon your knowledge of group theory you have already studied in your previous courses. Of course, you have studied groups at intermediate level, you have studied groups at your bachelor level, even you have studied groups in your MSc class as well. So you very well know definition of a group, definition of a subgroup, and then some immediate results. However, let me recall few of these. So let's define what a group is. You already know the definition, but it is just to recall. So let's have definition of a group. So definition. I'm sure that you understand this definition already, but let's just recall that. So a set G together with the binary operation, a set G together with the binary operation about binary operation, note that sometimes we use star for binary operation, sometimes we use symbol circle and different symbols for set of real numbers. When we consider it as group under addition, we use the symbol plus sign, and if we remove 0 from it, then set of real numbers, if we remove 0, it becomes group under multiplication, and we use dot for multiplication. But mostly in algebra we do not show the symbol of binary operation, and we call this notation as juxtaposition. It makes things to look very simple. So a set G together with a binary operation, we will denote it by juxtaposition. This means that we will not show the binary operation, but we would understand that binary operation is there. So denoted by juxtaposition. Is called a set G together binary operation is called a group. If these are the conditions, first of all, first condition you mostly call it closure law. So let me write it, closure law. We discussed it when we discussed binary operations in our previous session. So closure law means that if we take two elements of set G and we apply the binary operation, juxtaposition, we are not showing the symbol for that binary operation. So AB belongs to G for all AB belonging to G. So this is the binary operation to be closed under this binary operation. Secondly, that is associative law. Associative law, and you very well understand it. What we mean by associative law is A, B, C. We can say multiplied with. So A multiplied with BC is equal to AB multiplied with C, and this is for all ABC belonging to G. And thirdly, existence of identity element. Existence of identity element. So what we mean by this is that there must exist an element, we denote it by E mostly. There must exist an element E belonging to G such that E multiplied with any element A is equal to A multiplied with E is equal to A, and this is for all A belonging to G. We are denoting this binary operation by juxtaposition, but for just our convenience we are using the phrase multiplication. It does not make any difference if you understand what we mean. In fact, we simply mean the binary operation whatsoever it is. So this is the condition for existence of identity element, and then next condition is existence of inverses. Existence of inverses. So for any A belonging to G, there must exist an element. We denote this element. There must exist an element, and for this particular element, the notation we use is there exists an element denoted by, we write A minus 1. So this is just a symbol. There must exist an element denoted by A minus 1 belonging to G such that A multiplied with A inverse, or A operated with A inverse, is equal to A inverse multiplied with A is equal to identity element E. So if the set G has a binary operation and all these conditions are satisfied, then that set G is called a group under that particular binary operation. And let me write it that the element this particular element A minus 1 is called inverse of A, is called inverse of A. So having said that, let's note few results from your previous background about group theory. First of all, let me write it. We know that, in fact, we know these results from our previous courses. So we know that if G is a group and A, B are two elements of this group G, then we know that if we take inverse of A inverse, then result is equal to A. Secondly, if we multiply these two elements A and B with each other and we take inverse of this product, this is equal to B inverse A inverse. So this is from your previous knowledge. Now let's come to few examples. We have discussed quite a lot of examples in our previous session. Now let's discuss few more examples. And you are very familiar with these examples. Z, the set of integers. The set of integers. Then or the set of real numbers. The set of real numbers. And Q, the set of rational numbers. And C, the set of complex numbers. All these are groups under binary operation addition, and you know these groups very well. These are infinite groups. These are infinite groups. Each of these groups has infinite many elements. But we must say, to be very precise, cardinality of each of these groups is infinity. So these are infinite groups. Secondly, if we remove 0 from set of real numbers or minus 0, or we remove 0 from set of rational numbers, or we remove 0 means 0 plus iota 0 from set of complex numbers, then these are also groups under binary operation multiplication. In fact, we need to remove 0 because multiplicative inverse of 0 does not exist. And in our previous session, we discussed an example 0, 1, 2, 3, 4, and 5 under binary operation addition modulo 6. So we can generalize it. Zn is equal to 0, 1, 2, 3, so on up to n minus 1 is group under binary operation addition modulo n, and you know what addition modulo n is. And then we have discussed this particular set 1 minus 1 iota minus iota is a group under multiplication, and we discussed its Cayley table as well in our previous session. So this is a group under multiplication, and you may recall that we discussed two group structures on this set of 4 elements. So we have discussed two group structures on this particular set E, A, B, C, set of 4 elements. We took E as identity, then we defined two group structures. These are very important group structures. One of them is called Klein 4 group, and second one is fact cyclic group. You might be knowing these things from your previous courses. So we can define two group structures on 4 elements. And we also discussed a Cayley table. We discussed Cayley table for this particular set 2, 4, 6, 8, 10, and 12. And binary operation was multiplication modulo 14. So we did not complete that discussion. In fact, in our previous session, I can leave it as assignment for you. But anyway, we have discussed this particular set under binary operation multiplication modulo 14. So having discussed these examples, let's have a definition, and you know this definition as well, definition of a abelian group. So let's have the definition. A group G is called abelian group is called abelian group if A multiplied with B is equal to B multiplied with A for all AB belonging to G. So A group is a abelian group if the binary operation defined in the group is commutative. So, far as far examples are concerned, note that all the groups we have discussed above, in fact on this page, examples, all the groups discussed above, means on this page, are abelian groups. So all the above groups on this page, these are abelian groups. So these are abelian groups, but note that we have discussed groups which are not abelian. So let's discuss non-abelian groups. So non-abelian groups. So the first example we already know about non-abelian groups is D4 and D5. Dihedral groups. D4 and D5 are non-abelian. And you must have noted that in our previous session. You can again go back and note that these groups are non-abelian groups. In general, Dn for n greater than or equal to 3 is non-abelian group. So in general, Dihedral groups are non-abelian. Secondly, you know that the set of non-singular square matrices, you can take entries from any field, but from set of real numbers, is a group, and this is a non-abelian group. Let's note that the set of n by n mean square, in fact, n by n non-singular matrices. It's a very important condition, non-singular matrices with real entries. When I write real entries, it means entries of the matrices are real numbers. With real entries is a non-abelian group. And you must be knowing about this group from your previous knowledge, is a non-abelian group. And you know its name as well. This is called the general linear group. The general linear group. denoted by, and we denote it by a very special symbol. It is not denoted by general linear group because order of the maths is n by n, so we write n just at the end. Anyway, this is a non-abelian group as well. So general linear group is a non-abelian group. So having discussed these two examples of non-abelian groups, there are other examples as well. For example, there is a group called Quaternion Group. So let me discuss this group. Quaternion. Before discussing this group, let's discuss this group, Quaternion Group. Quaternion Group. About Quaternion Group, note that this is the group we call Quaternion Group. Consider Q for Quaternion and 8 because there are going to be 8 elements in it. So mostly this group is denoted by Q8. So these are the elements: 1 minus 1, I minus I, J minus J, and K minus K. So this is the set satisfying these elements, satisfy these relations, satisfying I square is equal to J square is equal to K square is equal to minus 1, and I multiplied with J is equal to K, J multiplied with K is equal to I, and K multiplied with I is equal to J, and then J multiplied with I is equal to minus K, and K multiplied with J is equal to minus I, and then I multiplied with K is equal to minus J. You might be recalling similarity with the IJK when you discussed vectors at your bachelor level, but anyway, it's very simple to memorize these things, and there is a help you can use, and it goes like this. You draw a circle and write IJK. Let's write it in anti-clock. You can write it clockwise direction as well, but anyway, in anti-clockwise direction, IJK, and then note that I multiplied with J is equal to K, J multiplied with K is equal to I, K multiplied with I is equal to J. So if you go anti-clockwise direction, this is going to be positive, but J multiplied with I is equal to minus K. J multiplied with I is equal to minus K. Then K multiplied with J is equal to minus I. Then I multiplied with K is equal to minus J. So if you go along the arrows, sign is positive, and if you go in the direction opposite to the arrows, the sign is negative. So it's very easy to remember this thing. To see how this set QA8 becomes a group, I have prepared Calais table for these elements. Let me show you that table. So this is the table. In fact, if I have to do it during the session, it would have taken a lot of time. So I have prepared it. So note that. So this is Calais table. for Quaternion Group. Quaternion Group, and we denote it by Q8 because there are 8 elements in it. So note that operation is multiplication. So 1 minus 1 I minus I, j minus j, k minus k, and then 1 minus 1 I minus I, j minus j, k minus k, and then I have multiplied with each other using these relations. For example, 1 is identity element. So you can see 1 is identity element. So all these elements are as these are above. Again, minus 1 multiplied with 1 is equal to minus 1. Minus 1 multiplied with minus 1 is equal to 1, and so on. I multiplied with 1 is equal to I. I multiplied with minus 1 is equal to minus 1 minus I. I multiplied with I is equal to I square. I square is equal to minus 1. Note that I square is equal to minus 1. And then I multiplied with j. Note that I multiplied with j is equal to k. I multiplied with j is equal to k. And you can see all these elements in the table are from this particular set. 1 minus 1, I minus I, j minus j, k minus k. So you can see that this particular set is closed